Without any further ado, I want to introduce today's speaker. So today's speaker is Shiraz Minwalla. He's one of the particle physicists. He's not going to bore you with materials, but going to talk about the very, very small things that the world is made of. Shiraz is from the Tata Institute of Fundamental Research in Mumbai, India. He did his undergraduate studies also in India at the Indian Institute of Technology, but then he came to the United States. He was a PhD student in Princeton, got his PhD in the year 2000, and then he moved on to Harvard University, where he had a temporal appointment as a postdoc, like most of us in our field, and he was a faculty member at Harvard before he moved back to India in 2009 and joined this Tata Institute of Fundamental Research in Mumbai. Shiraz has won many, many awards, way too many that I don't want to list them all to you. Many national, many international awards. The ones that are probably most famous in the United States is he got the New Horizons in Physics Prize. That's sort of the baby brother of what's called the Fundamental Physics Prize, which gives people $3 million, the real one. But no, apparently the committee has recognized that Shiraz is one of those people who will soon get one of those. And he also got the Presidential Career Award, which means he got to shake the hands of the president, I assume. And that was in 2003, so you can calculate yourself who that was. So without any further ado, Shiraz, please come here.
Thanks a lot, Andreas, and thanks to the organizers for the invitation to speak, and thank you for coming. A number of people have pointed out that I've spelled quantum wrong, and I probably typed that wrong, but you can't be sure. It may have been one of these irreducible quantum fluctuations. Okay. Okay, so the topic for today's talk is the search for quantum gravity. I've been very impressed by the sophistication of the questions that we heard in the interaction session before this talk. Nonetheless, and so I get the feeling that many of you don't need much of my introduction. Nonetheless, what I'm going to do for the first 6 slides or so of this talk is to introduce the question, to introduce what we're going to ask, and then try to explain the answer to the limited extent that we understand it. Okay, so let's start. Okay, so as was touched on in the interaction session, and as I now feel most of you know, theoretical physicists have developed increasingly sophisticated mathematical models to model many different parts of nature. Okay, so you have one model to model a substance called a superconductor, another model to model the flow of, let's say, water in a swimming pool, and so on. Okay, but there's a wonderful thing about physics, and that wonderful thing is this. It's that all the very many models we have for different substances are underlain by a few universal frameworks. Okay? Now, by a framework, what I mean is this: a mathematical structure and a set of rules to allow you to go from the mathematics to what you actually observe. A set of interpretative rules to go from mathematics to reality. Okay? So there are a few basic frameworks that underlie all of the models of physics, that model all the vast variety we see around us in the real world. My talk is going to talk about 2 of these frameworks, the 2 that always appear on David's admission committee statements of purpose. The 2 frameworks are called quantum mechanics and the general theory of relativity. Okay? As you know, these 2 frameworks were both developed about 100 years ago, at the beginning of the last century. And my talk, these 2 frameworks are going to play the star roles in my talk. So let's start by introducing these frameworks. The first of these is the framework of quantum mechanics. This framework was developed between, let's say, 1900 and 1930. It's a framework that I'm not going to introduce in any great detail, except to say things that most of you already know. It's a change in the mathematical structure of modeling the world, and it's a change in the way we view the world. You know, the framework of physics before this was that things had definite values. The quantum framework gives you probabilities for measuring various values. And that already sounds dramatic, But the difference at the level of mathematics is even more dramatic. It completely changes the mathematics of physics. Okay? This quantum framework, the framework within which things are fuzzy, the framework within which you type quantum and it spells the other way around, okay, is the basic grammar that has been used in particular to construct all theories of particle physics that those of you who were in the interaction session heard so much about over the last 80 years. Now let me say a little bit more about that. In more detail, modern theories of elementary particle physics, the physics of the very small, are set within the framework of what's called quantum field theory. Andreas said that he would not tell you what quantum field theory is. I'm going to try in the next minute or two. Okay. You see, quantum field theory, like much of physics before Einstein, even though quantum field theory comes after Einstein, but anyway, quantum field theory is set. The first thing to say about quantum field theory is that it's describing physics that's set on a stage, and that stage is spacetime. Okay? Spacetime you can think of as a grid or a sort of stage on which things happen. Things happen at definite locations, and they happen at definite times. Now, the thing about quantum field theory is that in quantum field theory, that stage of spacetime is just something that's given once and for all. You set it up, things happen on it, but it does not move. Okay? That's the first thing to say about quantum field theory. The second thing to say about quantum field theory is that it's quantum mechanical, as its name indicates. It describes these fuzzy things, things which don't have definite values. The third thing to say about it is that it's more difficult to study than what people more simply call just quantum mechanics. And the reason it's more difficult is that it's got a lot more degrees of freedom. Well, what is a degree of freedom? A degree of freedom is a variable you have to keep track of if you want to understand what's going on. Okay? So in simple systems of quantum mechanics, or classical mechanics, if you were throwing a ball and you wanted to know where it would be a little time later, the degrees of freedom are the position of the ball. You have to keep track of where that ball is and how fast it's moving at every given point of time. So that's a few degrees of freedom. It's not hard to keep track either classically or quantum mechanically. Now, in a quantum field theory, there's one, or more precisely a few, degrees of freedom associated with each point in space. Now, as you know, the number of points in space is infinite. Okay? So quantum field theory has an infinite number of degrees of freedom. Okay? A variable at each point in space. And if you want to study what's going on, you need to keep track of all of these degrees of freedom. Okay? That's what makes it sort of difficult. Okay. However, there's an organizing principle within quantum field theory that reduces the level of difficulty. And that organizing principle is this. It tells you that different degrees of freedom do not interact with, that is, affect, other degrees of freedom except those in their neighborhood. So a degree of freedom here affects what's happening here only because it sends ripples through neighboring degrees of freedom to affect what's going on there. That greatly simplifies what's going on. You see, this principle, what's sometimes called the principle of locality, the principle that degrees of freedom only affect what's happening in the neighborhood, takes this very complicated sounding structure and makes it simple enough to sometimes analyze practically. Okay? So quantum field theory is this structure with quantum mechanics, with degrees of freedom at each point in space. It's the grammar within which all theories of particle physics that have been written down to date over the last 80 years has been worded. Okay, so we met the first player in our story, quantum mechanics, and more precisely, quantum field theory. Great. The second character in our dramatis personae is gravity. Okay, now our modern understanding of gravity is through Einstein's theory of general relativity. And I'm going to introduce Einstein's theory of general relativity to you with roughly the level of detail that we talked about quantum field theory. So the first thing to say about Einstein's theory of general relativity is it's not a quantum theory. It's a classical theory. Okay? Within that theory, things have definite values. There's no fuzz. There's no uncertainty. Okay? In that way, Einstein's theory of general relativity is a step back, not as good as quantum field theory. Quantum field theory is more sophisticated in that sense. However, the second thing to say about Einstein's theory of general relativity is it's also a field theory, which again means that there's a degree of freedom, or a few degrees of freedom, variables you have to keep track of, at each point in space. However, this is an easier theory to keep track of things in each point in space, because these degrees of freedom are classical. They're just numbers. Okay? They're not these quantum fuzzy things, which are harder to keep track of. Okay? So it's a classical field theory. However, the thing about Einstein's theory of general relativity that makes it more interesting, that the direction in which it's more interesting than a quantum field theory, is this. The degrees of freedom that appear in Einstein's general relativity are not, well, the polarization of some electric field or something like that. That's pretty interesting in itself. But these degrees of freedom are the degrees of freedom that tell you about the geometry of space and time itself. Within Einstein's theory of general relativity, the first thing that we said about quantum field theory is not true. You see, the first thing we said about quantum field theory is that quantum field theory takes place on a stage that is set up once and for all and never changes. The degrees of freedom of Einstein's general theory of relativity are the geometry of the stage. And within Einstein's theory, as stuff happens on the stage moves around. Okay? So stuff happening affects the stage, and the stage moving around affects stuff happening. Okay? So here we have it. We had quantum field theory set on a non-moving space-time, fuzzy degree of freedom at each point in space, fuzzy quantum mechanical. Great for particle physics. We have the general theory of relativity, classical, but describing the dynamics of the stage of space and time itself, interacting with other stuff. So you see that each of these two frameworks, these two marvelous frameworks that were developed in the last century, has a flaw. Okay, quantum field. Okay, let me say this in more detail with the slides. Quantum field theory has been spectacularly successful in describing subatomic scale physics. David told you about, in the interaction session, about how LHC has been very disappointing because everything it gives us agrees with our theories. This is a fantastic vindication of the power and predictive power of quantum field theory. Just to illustrate that, there's this quantity called the fine structure constant. What it is doesn't matter very much, of the electron. Okay? This quantity has been predicted using quantum field theory to be this quantity. Okay, 137.035999166. Okay, it's fixing something. Okay, experimentally measured to be something else. The degrees of the two decimal places occur after lots of significant digits get it right. Okay, actually, I should have actually put the fine structure. Anyway, it doesn't matter. The point is that it's an extremely efficient and effective way of predicting things and gives experiments perfectly right. Okay, great. So quantum field theory is absolutely wonderful for particle physics. On the other hand, the general theory of relativity, the other framework that we've talked about, has also been spectacularly successful, but in modeling different phenomena. The general theory of relativity has been very, very successful in modeling larger scale phenomena in scales ranging from kilometers to the size of the universe as a whole. In fact, Einstein's theory of general relativity gave us a scientific framework within which we could ask questions like, how is the universe as a whole evolving? Okay? And it's been spectacularly successful in addressing those questions. So here we have it, two enormously successful frameworks. Quantum field theory for particle physics, general relativity for many things, but including cosmology. Quantum field theory also for condensed matter physics, though that will not be the focus of my talk. Okay. Okay, but as we've you know, as you've realized, everything's not hunky-dory. Because both are very successful frameworks ignore something that we know to be part of the real world. Quantum field theories ignore the fact that the geometry of space and time is dynamical. And we know that because the theory that describes the dynamics of space and time so wonderfully describes, for instance, cosmology or your GPSs. Okay? This phenomenon, this fact, is not put into the framework of quantum field theory. On the other hand, the general theory of relativity, which has the advantage of taking into account the dynamical nature of space and time, ignores another fundamental fact about reality, namely that things don't have definite values, that things have a quantum fuzz. Okay? So, great, agree with the experiment, but neither seems complete. Because both frameworks ignore something we know to be there in the real world. This, you know, for many people in this room, many of the theoretical physicists, you don't need further arguments. This is enough. It's not a state of affairs that we can allow to continue. However, but if you're more practically minded, as some of my colleagues often are, you might ask, okay, that's all very well, but for what practical question do you need to do better than quantum field theory and general relativity? What question do you want to answer what question do you want the answer to that our current frameworks are not sufficient for answering? Now, you know, there's a very good answer to this question. And that answer is that there is an event that happened in the universe. And there is an event that seems very important. And that is the birth of the universe. You know, if you want to ask the question, how did the universe begin? Very likely, if you want a scientific answer to that question, very likely you will need to understand the quantum theory of gravity. So I'm going to take a slide to explain what I mean in more detail. You see, the laws of physics have the following character. They allow you to if you measure what is there now, they allow you to predict the future. That is the purpose in life of the laws of physics. Take the present and predict the future. Okay? However, there's an interesting fact about the laws of physics, at least at a fundamental level, that they have a symmetry that allows you to interchange the past and the future. So, you know, the laws of physics are as good at predicting the past as they are at predicting the future. So suppose we wanted to know the answer to the question, how did our universe begin? Why should we know the answer to this question? Well, just because we all want to know the answer. Okay? If you want to know the answer to that question, how did the universe begin? One way to try to answer this using the scientific method is to measure what the universe is like now. Along a light sheet, actually, but it doesn't matter. Measure what the universe is like now, and then use the laws of physics to predict what the past was like. Okay? So the laws of physics can allow you to take what you see now and to make a movie in your head, running the history of the universe backwards. So what is the universe like now? The universe, like on large scales, there are lots of galaxies. These galaxies are all moving away from each other. Now you take what we see, plug it into the laws of physics, and produce a movie to see what the universe was like run in backward time. Now instead of the galaxies all going away from each other, in backward time the galaxies all coming towards each other. And then you run this movie, you keep going, until you get to a point where things really get interesting. The universe has got to something very, very small, 10 to the power minus, let's say 15 centimeters small. Very, very small, very, very hot, very, very dense. Okay? Everything that we see now was packed into that little bit. And you want to know, now what happened? What came before that? And the answer is, we don't know. We don't know because the movie starts getting fuzzy. Because the laws of physics that we use to make this movie are no longer valid when we get to this extreme situation. If we want to run this movie further back, we need better laws of physics and very likely the quantum theory of gravity. Okay? So very likely, if you want the answer to the question, how did the universe began, we're not sure. We'll never be sure till we know the answer. But very likely, you will need the quantum theory of gravity. Okay, so this is one practical reason, I mean quote unquote practical, okay, a practical reason to want to know, want a quantum theory of gravity. Great. So now we're all motivated, right? We all want the quantum theory of gravity. So let's go about and try to find it. Well, you see, these motivations were clear to everyone for a long time. From maybe 90 years ago, people were trying to find a quantum theory of gravity. And there's been, as I will describe as we go on, very limited success. And you might ask, why is that? Okay, one answer might be we're just not, we're not doing our job. But why not? Physicists have done understood many other difficult things. Why has quantum gravity proved so hard to crack? And there's an answer to this question. And the answer to this question is that we have very limited guidance from experiment in the search for quantum gravity. You see, when we do these wonderful particle accelerator experiments that we've been talking about in the interaction session, the fact that gravity is quantum in principle affects things. But it affects things so little that it doesn't affect the answer to the experiments that are currently performed. Now, it's an interesting fact that as energies of things you're banging together go up, these quantum fluctuations are more and more important. But as David said in the interaction session, we would have to raise the energies of our machines by something like 10 to the power 15. 1 with 15 zeros. Before the quantum fluctuations of gravity start becoming truly significant so that they stare us in the face. Okay? And every order of magnitude raise in energy is billions of dollars and lots of ingenuity. It's not going to happen in my lifetime. It's 10 to the 15. Okay, so particle accelerator experiments don't help. What else can we do? How else can we get data from experiments? Well, we could try to be clever. I told you that the beginning of the universe likely knew about quantum gravity. If so, if we were smart enough, we could use what we see now and try to deduce what the quantum fluctuations of gravity were at the beginning of the universe. Because, depending on what the precise nature of those fluctuations were back then, that affects what's happening back now. That's the nature of physics, right? The past predicts the future. However, if you think about it, a lot has happened in the universe in the last 13.6 billion years. Matter has formed, galaxies have formed, stars have started burning, black holes have banged into each other. And to disentangle what came from some subtle quantum gravity effects long ago from all this dramatic stuff is not going to be easy. Actually, for a particular possible quantum gravity effect, it turns out to be easy. It turns out there's a miracle which allows plausibly it to be easier than we suspect. But to get detailed information is not going to be easy. Okay, that particular quantum gravity effect is detecting spin 2 polarization in the CMB. I won't go into that. Okay, but okay, great. So if we're very clever and very able to solve our equations, we could look to see what's now and deduce what the quantum fluctuations of gravity were like at the beginning of the universe, but that's not going to be an easy task. Okay, particle accelerators don't work. Beginning of the universe is not much help. What else? Are there natural places in the universe where quantum gravity effects are important? Turns out that there almost certainly are. At the centers of these black holes that David was talking about, that collided and did these wonderful things. At the centers of these black holes, very likely there's a place where quantum gravity effects are very, very important. So that sounds great. Sounds like we should put in a proposal to the Trump administration, asking them to fund an experiment that will allow us to send a spaceship into the center of the nearest black hole. But the problem is this. If you find a PhD student to go into that spaceship, he can do the experiments, but he'll never be able to publish his results. Because you see, the interior of the black hole has the following property, that information, at least classically, never comes out of it. So you discover all about quantum gravity, but you can't let us know. Okay, so black holes don't help, and so on. You see, so quantum gravity seems like a conspiracy of nature. Nature is trying to shield the secrets of quantum gravity from us. It's doing it very effectively. We don't have too many experimental clues. So what are we to do? Well, you know, if you were really pragmatic, you would say, well, this sounds like a problem for 1,000 years from now, so let's work on something else. Wait for 1,000 years, somebody clever will get experiments. The great thing about human beings is that human beings are not pragmatic when it comes to intellectual questions. That's totally unsatisfactory. So what do you do? So what physicists have decided to do, what string theorists have decided to do, is to take inspiration from the parable of the physicist and the spherical cow. Let me tell you the story for those of you who have not heard it. The story goes as follows. There's a farmer who's got a prize cow which produces a lot of milk, and then suddenly that cow starts doing less well. It's producing less and less milk. The farmer gets worried, but very luckily he has a brilliant physicist friend. So he thinks, I'm in good shape. I'll ask my physicist friend to help me get more milk from the cow. So he calls the physicist and says, this is my cow, and he's not producing as much milk as he should, and what do you think is the issue? So the physicist says, well, let me model this cow as a spherical cow. Let me assume in my model that the cow is a sphere. At which point the farmer, being a smart, practical man, says, please model it on somebody else's cow, and goes away. Because you see, the idea that the cow is a sphere is ridiculous for practical purposes. But that's how physicists function. When faced with a problem that is too hard to solve, what you do is try to change the problem to something that has some features in common with the earlier problem, but that you might be able to solve. And then, hopefully later, try to make progress. So that's what string theorists have done over the last 50 or 60 years, and I'm going to tell you a little bit about it. Okay, so I have just one framework on this. So, I told you that the problem of trying to find the quantum theory of gravity in our universe, the place we inhabit, is so difficult because we have so little guidance from experiment. So what string theorists have done is to take the following tactical retreat. The question we've set ourselves is this. Can we find even one consistent mathematical theory that has both quantum mechanics and gravity in it? What does it mean for it to have gravity in it? It means that at low enough energies, you get an almost classical theory of fluctuating spacetimes obeying Einstein's equations. What does it mean for the theory to be quantum mechanical? It means that everything, including spacetime, is fuzzy. Okay, that might at first strike you as an easy thing, but it's not. It's proved surprisingly hard. Okay, the problem of trying to do something like this has been around for forever. It's proved surprisingly hard to find even one consistent theory, mathematically, logically consistent theory, which has both quantum mechanics and fluctuating spacetimes. Luckily, we have a few similar theories. Okay, and these theories were obtained using the string framework by a then very young Argentinian string theorist named Maldacena in 1997. And in the rest of this lecture, I'm going to explain this construction to you, the construction of the one class of successful quantizations of gravity. Remember, I warn you, this is the spherical cow of quantum gravity. We're not going to describe the world in which we live. Okay, it's a toy model. But I'll hope to convince you by the end that we'll learn something from it. Okay, so in the rest of this lecture, I will describe the complete formulation presented by Maldacena of one model of quantum fluctuating spacetimes. Okay, now, for you to understand how incredible this model is, it's useful to contrast it with other successful quantizations, not of spacetime, but of other things. So let's go back to 70 years ago, 80 years ago, when in the cutting edge triumph of theoretical physics at that time, theorists managed to produce a quantum theory, a fluctuating theory of Maxwell electromagnetism. Maxwell electromagnetism, as many of you know, is the classical theory that describes how charges attract or repel each other, describes magnetism, describes the propagation of light. This theory was discovered by Maxwell maybe 150, maybe a little more than that, years ago. It was a classical theory, much like Einstein's theory is now a classical theory. And in the 1940s and 50s, a bunch of theorists, including Richard Feynman, whom many of you have heard of, were successful in completing the program of quantizing electromagnetism interacting with charged particles. Okay, so I'm going to give you a 1-minute summary of how the answer to that program went. So first, what is classical electromagnetism? That's a classical field theory. Now all of you are experts in what that means, right? It means there's one or a few degrees of freedom in each point in space. It means these degrees of freedom have definite values. And it means that the mathematical structure of describing this is differential equations, relatively simple mathematical structures. Okay? This triumph, let's say by 1950, maybe a little earlier, was the construction of quantum electrodynamics, a quantum version of this classical theory. And it's a fabulous thing. But if I try to describe it conceptually to you as I will now, the answer is surprisingly simple. Corresponding to every classical degree of freedom, every one of those numbers at each point in space that you have to keep track of in Maxwell's theory, there is a corresponding quantum degree of freedom. The correspondence is very clear. It's a one-to-one map between the classical and quantum degrees of freedom. And instead of all these classical degrees of freedom interacting according to Maxwell's equations, there are these quantum degrees of freedom interacting according to what is a very close cousin of Maxwell's equations. So when you look back after all that hard work and it's all put together, you can't help feeling a little disappointed. That's it. The final answer does not sound very dramatic. For every classical degree of freedom, you replace it by quantum degree of freedom. Okay, that's how it was. Now that you understand this, let me explain the answer for quantizing one particular spherical cow, one particular toy model of quantum gravity. Okay, one particular model of gravity. Okay, now these slides are going to look technical. I've just put these equations there to appear cool, okay? It doesn't matter very much. They're names. Many of these things are just names. Okay, but I'm going to anyway tell you a little bit about the slide. Okay, what we're going to do is to describe the quantum theory of gravity. This is type 2b supergravity for the experts, propagating in a 10-dimensional space. So you see, our spherical cow is very spherical. Okay. We're not gonna we're gonna change not just little details like the mass of the electron and so on. We're going to change the number of dimensions in which our quantum theory of gravity lives. It's not going to live in 3 space and 1 time like we do as far as we can see, but it's going to live in 10 dimensions. Moreover, this 10-dimensional space has an interesting sort of geometry. Now, this 10-dimensional space is an interesting geometry. The geometry of the space breaks up into what mathematicians like to call the product of 2 different geometries. So 5 of the dimensions behave one way, and the other 5 behave another way. One of these, the first 5, in the ambient space, when the theory is not doing anything, live in what's called a 5-sphere. Now 5-sphere is very easy to understand. You see, a 2-sphere is the locus of all points equidistant, let's say at unit distance from the origin in space. This all of you know. A 5-sphere just goes like this. Imagine a 6-dimensional flat space and consider the locus of all points at unit distance away from the origin in that 6-dimensional flat space. Hard to imagine, but easy to work out in mathematics. Okay? So this part of the space is easy. It's just a 5-sphere. This part is less familiar to you. It's got a name. It's called ADS5. I won't say much about it, other than the fact that it, unlike the 5-sphere, includes time. You see, all known physics has time in it, and exactly one time. So when you have 10 dimensions, that means 1 time and 9 space. The time lives here. The S5 is just space. Okay, great. Now, so Maldaceno's great accomplishment when looked at with some eyes was to answer the question, what is the quantum theory of classical gravity propagating in area S5 cross S5? And the answer to this question was not take every classical degree of freedom. These classical degrees of freedom in Einstein's gravity are called metric fields. It was not take every metric field and replace it by a quantum metric field. That would have been boring. The answer was totally unexpected. Okay? The answer was that the quantization of this space was given by a 4-dimensional quantum field theory. A 4-dimensional quantum field theory. A 4-dimensional quantum field theory in which the basic, which has a name, it's a fancy name, you can forget about it. But the important thing about this field theory is that the number of degrees of freedom living at each point in space, all these degrees of freedom come as n cross n matrices. You know, a matrix is like an array. It's got rows and columns. The size of these matrices are n cross n. And the quantization proceeds in a limit where this n is very large. Okay. So many things about what I said should strike you as crazy. Okay. Firstly, I spent the whole first part of my lecture trying to tell you how different quantum field theory was from gravity. Then I told you we're going to try to solve the problem of finding a quantum theory of gravity. And I'm telling you that the answer is a quantum field theory. Just sounds like I'm contradicting myself. The second thing about it that should strike you as crazy is that the theory that my spherical cow theory of quantum gravity, of gravity lived in 10 dimensions. My answer lives in 4 dimensions. How can that be? Okay, so this just sounds mad, and I think that much of the physics community, much of the string theory community, when Maldaceno first published his paper, thought, oh boy, this guy's lost it. Okay, however, it's correct. Okay, we've had 20 years to test this conjecture in many, many different ways, and we're sure it's right. So I'm going to tell you a little bit about how it's right. Okay, this is going to be the most technical slide in my talk, and I'm sorry if it feels incomprehensible, but let me just say it anyway. Okay, you see, there's this mathematical thing that's been known for a very long time, for maybe 40 years, 40, 50 years, that when you take these quantum field theories, and these quantum field theories are objects like the one I'm talking about, where the basic degrees of freedom that live at each point in space are matrices, arrays, and the size of these matrices are very large, then it's been known for a long time that there is a sense in which, in the large n limit, the size where the matrices become very large, this quantum theory becomes classical. This was first precisely stated by a great theoretical physicist. We can argue about how he compares with Wilson, whose name was 't Hooft. Okay. Now, so it's, this interesting thing. I say one more thing. You see, quantum theories have a parameter called Planck's constant, called h bar. Okay, and anyone who studies quantum mechanics, the first thing you learn is in the limit where this Planck's constant becomes very small, the theory becomes classical. This is the standard classical limit of quantum mechanics, and it's the limit that the people who understood how to quantize, who make quantum electrodynamics, exploited in making that quantum theory. They made a quantum theory which was such that when you took h bar to 0, you recovered the classical theory. And this is somehow an easy thing to do. However, we've known for a long time that there's another way to make quantum field theories classical. That is, have their degrees of freedom be very large matrices. This has been known for a long time, but this is a more complicated classical limit in the following sense. This h bar goes to 0 limit, what classical theory you get when you take h bar goes to 0 is obvious from the formulation of the quantum theory. You look at the theory and you know what classical equations you'll get when you take h bar to 0. On the other hand, when you have these theories with these big matrices and you take n to infinity, you get another classical theory. But what theory you're going to get, you know it's going to be classical, but what theory you're going to get when you do this, take these matrices to be very large, generally speaking, you have no clue. Okay? I think until Maldasena's work, everyone had assumed that the large n limit of reasonably interesting theories, like n equals 4, d equals 4, super Young's theory, would be a classical mess. Some non-local, very complicated stuff that would be classical but useless. Instead, what Maldacena explained to us was the classical limit, this large n limit of this quantum field theory, was given by a classical theory, which was not some non-local mess, but was governed by the most beautiful equations ever written down by human beings, namely Einstein's equations of general relativity. Except that these Einstein's equations of general relativity, well, general relativity propagating in 10-dimensional space in this ADS 5 cross S5. Okay? So it's a totally remarkable statement. It's a totally remarkable statement that you take a large n limit of a particular quantum field theory in 4 dimensions, and out comes dynamical propagating 10-dimensional space-time. This space-time is classical in the limit that n is strictly infinite. If n is very large, let's say a billion, not strictly infinite, if you looked at what happens to that space-time, it fluctuates a little bit. It becomes quantum. Okay? But if n is made smaller, let's say you make n equals 2, you ask what happens to the space-time? And the answer is, well, it's just not there. Space-time emerges in the large n limit of this quantum field theory. It is an emergent fact about this quantum field theory that is precise when n is large, becomes less precise, and that less precision is fluctuations. Okay, when n becomes smaller, but when n becomes some small finite number, there is no real sense in which there's any space-time at all. You know, my PhD advisor liked to summarize the lesson of this with the following words. Says the words went something like this: when all is said and done, we will discover that space-time is an illusion with no real reality, just some approximation of more fundamental reality. Okay? The reality of this model is the fields in this 4-dimensional space-time, these n cross n matrices. When n is large, that's about the same as things propagating around in fluctuating space. When n becomes 2, there's no real sense in which that space-time exists at all. Okay, so this is what I said. Therefore, within this model, there's a sense in which, now one should take this too seriously, okay? This is poetic license. There's a sense in which space-time is an illusion, an emergent notion that has precise meaning only at very large n. However, the precise mathematical structures of the theory at any finite value of n have nothing to do with space-time. They've got to do with degrees of freedom of a quantum field theory in 4 dimensions. Isn't this remarkable? Okay. This is a lesson we've learned from one consistent spherical cow quantum theory of gravity. We don't know that the same is true of the quantum gravity in our universe. But note that we've spent 80 years maybe, or what, you can argue about that, many years trying to find one consistent quantum theory of gravity. This one and its close cousins, all we have. So if we were to extrapolate from limited data, you know, I would guess that this is true of our world as well. Okay, at a much more mundane level, all of this suggests a completely unanticipated role for theories of gravity. You see, I've told you the right way to quantize gravity is by a quantum field theory. Now, most physicists don't care too much about quantum gravity, but many of them are very interested in understanding how quantum field theories work at very strong values of what's called a coupling. It doesn't matter what it is. Some quantum field theories, even though we think we know how to define these theories very well, very hard to solve. Now, you can turn what I said around. You see, there's this fantastic fundamental statement that the way to quantize gravity is via quantum field theory. But there is a practical statement as well. If you want to understand how a quantum field theory works at what's called very strong coupling, doesn't matter what that is, if the quantum field theory is of the sort that has many degrees of freedom, these large arrays, then the best way to understand how the quantum field theory works is by solving Einstein equations of gravity. Okay, classical equations of gravity. This is also incredible. You see, because it's a unification of what was thought of as two completely different areas of physics. And it's given rise to what, maybe this is not an accepted name, but I think it should be, a new area of study called applied gravity. Gravity in service of other areas of physics. If you're a physicist, you don't give a damn about gravity, but you want to know how your quantum field theory works. It could be that in the right situation, the best way to answer that question is by solving Einstein's equations of gravity. This is another stage in this unification of the structures of physics. We started this talk by saying there were two different structures, quantum field theory and gravity, and now we see that actually, at least in this toy model, they're the same. Okay, fine. Several aspects of the story I've outlined above remain unsatisfactorily understood. To start with, the fact that this mouthful name of quantum field theory reduces to 10-dimensional supergravity at large n has only been established within the string framework. However, quantum field theories we understand in their own right. So, if we were smart enough, we should be able to start with our description of quantum field theory, and show that in the large n limit, this gravity theory emerges. We haven't been able to do that. In other words, why we know this happens, because we've tested it in many different ways, we don't really understand in detail precisely how space and time, fluctuating metrics, emerge from strongly coupled gauge dynamics. And it seems likely that we'll learn many important lessons by filling this gap. Okay. Now, all of my lecture, beyond the introduction, all of my lecture has been about the formulation of one, or really a class of, non-trivial quantum theories of gravity. Already, by understanding this one example well, we've learned something quite remarkable, I think. And that is that the quantization of gravity proceeds in a way that nobody had previously anticipated. It exploits a different classical limit from h bar goes to 0. It comes from these large n matrices, and within this framework, space-time is an approximation. Okay, now the string framework has zillions of consistent quantum theories of gravity, each of which is an answer waiting for a question. Okay, what is the question whose answer gives you in the classical limit that classical theory of gravity? We've got zillions of answers waiting to be addressed. We don't know what questions they answers to. We've learned so much by pairing up one set of questions and answers. It seems very likely that every additional one will teach us even more. So there's enormous amount to be learned. Great. However, we're still in spherical cow land in everything I've said so far. Of course, in the end, in order to address questions about the birth of our universe, we don't want a spherical cow quantum theory of gravity. We want the theory of quantum gravity in our universe, the fluctuations that our universe has, the ones in the universe in which we live, not in some toy model. Does the quantum theory of gravity of the real world lie within the string framework? If so, where is it? How do we identify it? How do we understand this theory? I don't know the answer to these questions. I think nobody does. I don't know how we're going to get the answers to these questions. But perhaps there's some unexpected experimental input that will come from somewhere, maybe from studying cosmology or cosmic strings or God knows what, something nobody's dreamt up so far that will help us. I just don't know. Okay, so that's it. I'm sorry I've kept you. Oh, maybe I've not kept you over time. Okay, and that's a first. Okay, so let me summarize. Okay, I think I've tried to explain to you that the problem is to find a quantum theory of gravity. For the more practically minded, quote-unquote practically minded of you, I try to explain why we need a quantum theory of gravity. We likely need it to understand the birth of the universe. I told you about string theory, an exciting but incompletely understood framework within which you can set quantum theories of gravity. And I told you how the string framework has led to the complete but surprising formulation of a class of, I really described one of them, 10-dimensional quantum gravity systems. And the answer was a big surprise. The answer was not quantum variables for these classical metrics, but was a quantum field theory in some lower dimension. The result is a great surprise. Space and time are emergent notions, not fundamental notions within the mathematical framework we understand. And there's a sense in which, with poetic license, space-time is an illusion in these models. It has precise reality only when a parameter is taken to infinity, to any finite value of the parameter. It's not precise. Okay. The complete formulation of other gravitational systems is an outstanding formal challenge. And the really interesting question, I mean the really important question, is the formulation of the non-spherical cow quantum theory of gravity. The quantum theory of gravity in the world in which we live, we don't know how we're going to get there. Thank you.
We have time for a few questions if you want to know more from Shiraz. And I was supposed to remind you, please repeat the questions that we have.
Yes.
Apparently, there is a vacuum energy in the universe out of which pairs of particles can spontaneously appear. And is it possible that quantum gravity could be implicated in that process, and that process used to as an experimental basis for investigating?
Okay, that's a great question which has many different elements, and I'll take them one by one. Okay, firstly about vacuum energy. There are two things that happen, both of which are very interesting, and let me address both of them. The first thing is, just at the classical level, it appears that our universe has what's called a cosmological constant, which is a fancy way of saying that empty space is filled with some energy. Okay? This is just a simple classical phenomenon as far as we understand, just at the classical, not as sophisticated as measuring particle fluctuations, just at classical level, our universe appears to have this positive energy density. And understanding why this is the case, more precisely, why the energy density has the value that it does. You see, it's a very strange energy density, because in some unit, some way of measuring it, it is 10 to the power 120 times smaller than the natural scale, energy scale that enters gravity. Okay? Any quantum gravity person, if he didn't have access to the fact that the universe is a place in which you can live, if he was somehow decoupled from the universe mentally, if he were to estimate how big the universe would be, he would come up with the estimate 10 to the power minus 33 centimeters. Okay? This energy density, which sets, in some sense, the scale of the universe, is an energy density that gives you a universe of size, I'm being imprecise, but anyway, it gives you a universe of size 13.6 billion light years. So the question of why there is a non-zero energy density and why it has this value is a very important problem in the study of gravity, probably in the study of quantum gravity, and is one of the central, likely one of the central experimental clues we have about that theory. We don't understand it at all. Okay, but it's okay. Now your question had a second element, which talked about how the vacuum is forgetting about this very low energy density, which is only important for the large-scale structure of the universe. If you take a little bit of the vacuum in a lab, you will see that it's not quite a vacuum in which nothing's happening. Okay, particles and antiparticles are constantly being pair-produced. Now, this is a phenomenon we understand very well. It's a phenomenon you can model and completely calculate within ordinary quantum field theory. Presumably, gravitons are also being pair-produced. That is something that would be very, very hard to measure. It's far beyond our experimental capabilities. So that would not. So this does not by itself give us a clue about quantum gravity. However, there is a third element to your question, which might give us a clue, and it goes this way. You see, when particles are being pair-produced in our lab, we understand that very well. We also understand very well what happens when these particles are being pair-produced in any region of space-time that is sort of nice. Now let's take a little region of space-time that's at the event horizon of a black hole. Locally, it's quite nice. So we understand more or less what's going on, we can predict what's going on. But the final result of our prediction is very strange. This was a prediction actually made by Stephen Hawking, the great British physicist who passed away recently. He realized that if you use the rules of quantum field theory, which we think we understand, in the neighborhood of the horizon of a black hole, you find that these pair-produced particles, one of which has, in some colloquial sense, negative energy, shoots into the black hole, while the other thing, which has positive energy, comes out. Now, all of these pair-produced particles are like electrons or photons, nothing to do with gravity, or also the gravitons, but we don't see the gravitons. The gravity is not, the fact that it could be gravity is not so important here. But what's important is that this black hole effectively radiates at the quantum level. And the fact that black holes radiate give rise to what seems like a paradox in physics. The paradox goes this way. You see, a black hole could be made up of very complicated stuff. Maybe my spherical cow went and collapsed and formed the black hole. Okay. However, what comes out as thermal radiation to the best extent to which we can do the calculation. So it appears that time evolution has lost information of what went in. And this negates all basic principles of physics. The point in life of physics is to take past and predict the future. You can also go back. You should never lose information. It may be complicated to get it, but the information should be contained. The fact that when you put quantum mechanics and gravity together, quantum mechanics and black holes together, it appears that you lose information is a great paradox in theoretical physics. Can't be that the information is actually lost. We're doing something wrong, but we don't understand really what we're doing wrong. That is an important theoretical clue. A number of my colleagues spend all their time trying to do thought experiments with quantum mechanics and black holes to try to get clues about quantum gravity from there in some way. So your questions were all parts of the questions were bang on.